this talk is kind of a follow-up of the one about Pharo.js. And the end of Pharo.js, one of the perspective was like we need a middleware. So we started exploring this in this project. Actually, it's a quite old project that I revived recently. So over the years, in different contexts, I had to experiment. I made different applications, and I was involved in different applications for mobile, for web, for SaaS products, and for robotic applications. And what do these have in common? They're not much, but they all involve some kind of networking at some level. And if we can analyze to see what are the difference beside the functionalities or the platform, networking is also a difference because they have different architecture. So one client server, one is peer-to-peer, other is more local. And we can dig and we can, beside the architecture, they use different networks, they have infrastructure networks or ad hoc networks with different protocols. The protocols can be connected based like HTTP, TCP, or some WebSockets, or they can be disconnected if you are using UDP, unicast, multicast, broadcast, or whatever. And there are different communication modes. Sometimes you want asynchronous communication. You send the message and you wait for the response to come back, and you stop everything until you get the response. Sometimes you want just asynchronous, send it and forget it. And until maybe later you get a future response, and in case you need the response before, you halt and wait until you get it. Or the one-way request, this one really you forget completely about the response. Or you go streaming, you can one-to-one, one-to-many, and so on. And so this means different middlewares. And so what's the middleware anyway? So basically middleware meaning we have some networking and we have different images in our different software running on at least different processes, but usually different computers, and they are talking over a network. Here we have like I don't know if you can see the colors. They are, one is kind of blue and the other kind of greenish, and the blue one is sending a message over the network to the green one. At least this is the logical view. And what happens behind the scenes, it's somehow we go from that logical view to bits going through a socket over the network. And so the question is how we go from the logical view to the socket view. And traditional or in an object context, we represent the remote object through a proxy local to the same image, and it's the proxy that actually receives the message, and through a chain of changes converts it to bits and sends it over the socket. And on the other side, we have this gray object which is supposed to be a dispatcher, and it will get the data from the socket and reconstruct the message and deliver it to our green object, the actual receiver. And in case we have many potential remote objects, we use different proxies, and each one has an ID. We have here two objects A and B, and each one has, so the proxies knows about the ID and send it through the socket and deliver it to the other side. So, and this lower part with the proxies and dispatcher and socket, this is what makes the middleware. This is one kind of middleware. And and if we analyze the ecosystem, the Smalltalk ecosystem, there are multiple ones. I cited few of them. There are many others. So Seaside we can view it as a middleware. If you take the REST view, there is something called RST, Remote Smalltalk. So Pharo things, Seamless. We worked on, for the robotic part, there is something called Pharos. We use Ubiquitalk for peer-to-peer, and Pharo.js itself has some middleware. So we need to see what's, it's scattered, and my motto is always try to unite and find the commonalities and make things, as a small community, we need to join efforts and avoid addressing so many, scattered projects. So can we? But each of these middleware has a specific features and a reason why it was created in the first place, and they don't overlap. They have partially overlap on the idea, but not fully. So the question is, can we have one middleware? Hence the name of the project, one that gathers them all together. And so we need to analyze this middleware, and we see that there are different facets. So they have, like, obviously the networking. You have some take care of reliability, some doesn't care about reliability. So there are security issues, the way to deploy, the way you share, and so on. So each one can be decomposed. So for networking, you have protocols for how you encode and send data. We have discovery, how you know about there is somebody there in the first place. Communication can be, we can be either local communication or remote. We are doing RPC. So basically, we are sending a message to some target, or calling a procedure remotely. But they can be events. We can synchronous, asynchronous, sharing. We can have remote references, garbage collection, concurrency issues. We have deployments. We can static, on demand. We can have mobile code that moves from one place to the other, and then go on and on. With reliability, we have latency issues, bandwidth issues, disconnection, security. We need authorization, authentication, and we need obfuscation, and so on. And no one covers it all. And hence the idea of having a modular thing that, depending on what you need, you pick the right combination, or at least this is the dream. And I said these are the first step. My goal here is to share with you my current ideas and get your feedback, and hopefully go into the right direction. I managed to have something working a couple of days ago, so this is what I'll be showing. So the current design or ideas behind MyPrecious. So we want remote communication. Obviously, here we have 3 images that are talking somehow through a network. And when I say communication, in our context, we are in small talk, so we are doing messages. They're the only way of communicating. So the meaning that we have in each image, we have some objects sending messages to others located in other images. As I said before, the remote communication, the remote objects materialize as proxies. So here in the the left side of the slide, we have a proxy on the object in the remote image of the object B. So it's the proxy that takes care of transmitting over the network the messages. And how we implement a proxy, so this is nothing magical. So basically we try to create an easy implementation of a proxy. This is the standard implementation. There are more complex ones. The easy one is basically you create a nearly empty class, and it does not understand. And whenever you receive a message, capture the message, trap it, and transfer it to the network via socket to the other side. But we want some modularity. So in the current implementation of MyPrecious, there is this kind of, each proxy knows about an ID, obviously, so we know what is the target object in the other side, but we have a dispatcher. And the dispatcher is in charge of actually doing the work of transferring to the other side. So meaning that depending on the dispatcher we use, we can have one kind of some modularity here. So we reveal next step of our next layer of the dashed remote communication, the magic behind it. And so the proxy is talking to a dispatcher, and dispatcher is the one in charge of the remote communication and sockets if needed, and so on. And if we have different remote objects, meaning we have different proxies, but since the remote objects are on the same side, same image, so the proxies share the one dispatcher. So this is because it takes the dispatcher is in charge of the networking, and it's not specific to one proxy. There are differences depending on the ID, but that's it. So the ID of the proxy says, please deliver this to the remote object with this ID, and the dispatcher knows how to pack everything and send it over the network. But if we have different memory spaces, we need different dispatcher. Basically, each dispatcher is in charge of one memory space. Not sure about the next slide. Yes. So what the dispatcher allows, it allows for having multiple protocols. And I said here, if you notice, I said one sender or one dispatcher. It's actually per memory space and not per image. This is because we can have the same image on the same image accepting connection over different protocols. Here I have like the green image accepting connection through TCP, UDP, and WebSocket. So depending on the context or whom you are talking to, you can use one or the other. And you see here in this system, we have like 3 images, and we have like 4 protocols. So, and we can accept on one memory space, we can accept messages in one protocol and respond to another protocol, or issue, not respond, but send messages to the others through another protocol. Like the lower one, it accepts through HTTP, but then if it needs to talk to C, it will talk through WebSocket. So this is like okay, tried. The colors are faded, but hopefully you can read. So I try to make the class diagram. So the proxy knows the dispatcher, what actually it's called the remote dispatcher, and there are different kinds of so remote dispatcher is an abstract class, and we can have variation depending on the protocol. I mentioned 2 of them, TCP and UDP, but you can have as many as you want. And the dispatcher knows the address. So this is another entity I introduced in here, the address of the target. So depending if you are using a TCP remote dispatcher, you need a TCP address, obviously, and so on. And actually, why it's the way we constructed it the other way around. So basically, when I want to talk to a remote object I don't know about, all I know is its ID and its address. And from there, I reconstruct the remote dispatcher, if it's not available. If it's already available, I use it. So we have the remote dispatcher on one side, and we have the local, it goes through the network, but then on the other side, we have a local dispatcher that decides based on the ID to which target will deliver. And actually it does some more stuff. So this looks like the class diagram for the remote dispatcher, for the local dispatcher, sorry. Again, depending on the protocol it accepted, you will use one subclass or the other. And to actually handle the communication, you need to do some serialization, some marshalling, which, by the way, the other side do it too. This means that we need to have like compatible. Obviously, when you talk over the network, you need to be to use the same protocols. But I could not represent everything on our slide because at the end it grows and grows, and we have the color and the resolution issue. So I try to pack to isolate everything and have pieces here. Hopefully, you will reconstruct everything. So we talked about sorry, I have to get a sip of water, but we talked about remote communication in a small talk way, and so far we were discussing about the receiver and how we deliver the messages, but a message often has arguments. So assume on the left side we have an object that send a message through the network. So the big arrow here means like a remote communication. It's called it sends the message M1 with A as parameter, and A belongs to the first image. And B receives the message, and it will the implementation of the message M1. Basically, it sends M2 to the argument. Fairly classical, but we are doing it over the network. What happens? So if we are passing by reference, meaning that this is the normal way, the way we do it most of the time in a single image. So basically, we need to send back another message to the other side, which, by the way, means before returning or answering M1, we need first to get to the other side. So we can make, like sometimes it makes multiple round trips before you get the response. The other way of doing it is like we want to make a copy. Actually, A, from the left side, we want to preserve it, and we are telling B, okay, make a copy of A, so this should be implicit, and B that isn't aware it's getting a copy actually, but by construction it receives a copy of A, and so if it sends M2 to A, if M2 does some side effect, only the copy is impacted, not the original one. But this of course requires that we need class A deployed on this side too. So we did the message receiver, delivery, arguments, and now the last part of a message is a response. And a message we get a return value that can be passed by copy or by reference, like an argument, fairly normal. But what happens when we have an exception? So imagine I'm in a single image, and A is sending a message M to B, and M signals my specific exception, my domain exception. And we are aware of it, and we have a handler on the side of A, and basically it does on exception do something special. But now what happens if we distribute the same code? And what we want to have a better user or good user experience or developer experience is that we should not change the code because we change the way we distribute it. So this is what it means by distribution agnostic code. So what we do, we reify responses. So whenever you get a response, it's actually whatever response it is, we pack it into an object that sends it back. Almost finished. So we have two kinds of hierarchy of responses. So we have so far two kinds of responses: normal response, which is basically a value, and an exception response. So with whenever you receive a response object, the sender of the message that gets the response, it sends a message value to the response. Say, okay, give me your actual value. And if it's a normal object value, you get the actual object that was sent back. But if it's an exception, you have another exception that is signaled locally. So I recap what I said so far. We have A sending a message to B, and this execution of M, the message in the side of M, raises an exception, signals an exception that has some context. So what we get on on the side of A, we get an object that is a remote exception. And it has a proxy, so it remotely references the exception on the side of B, so we can remotely access the context. But it's still, the remote exception is still an exception, and it's still yes, it's an exception. It's signaled on the sender side, of course, but it accepts the same handlers and the origin exception. So this is an interesting discovery. I found out that you can trick the system even if your exception is not of. If you write this code, let me go back. If I have this code to the left with the handler, even if my exception is not in kind of my exception, I still have a trick or workaround to trick the system and make it still make a handler capture it, and so it's the code still works, and we are agnostic to distribution. Right. And yes. So this is what basically I was telling. So we are distribution agnostic, and that's it. So I have some old version of the code here. The current version, it's some branch, but it's dirty. I don't recommend you have a look at it, but I want to put it here because hopefully I clean up my code so soon, and make it available. And that's it. Thank you.
Thank you, Noury. Thank you, Noury.